Good morning, everybody. It's Dr. Gray. I wanted to walk y'all through the worksheet that you are going to be filling out in your lab on Monday. So this worksheet begins with a series of questions. Just a second. These questions are questions that I'm hopeful that you can answer at this point in time, either from the lecture that we just had or lectures that we've had in the past. This is all dealing with our enzyme lactate dehydrogenase, which is what we're trying to purify, and our product that we're observing the production of NADH. So I just want you to walk through some of those questions and answer them. You can answer them on a separate piece of paper. However you'd like to answer them, please do so. The one that I will give you, because if you Google this, you'll get a result that's a little bit different than I'm looking for, and not that it's inaccurate, but the units are going to be different. Question number 9, what are the units for the extinction coefficient of NADH? And number 8, what is the extinction coefficient for NADH? So NADH has an extinction coefficient of 6220. The units are significant, as it turns out, for the number that I provided y'all with, and that is centimeters, inverse molarity. So that is some information that I'll provide you, and that will be very important because what we're focusing on for this experiment is the Lambert-Beer law. A equals ELC. Absorbance is equal to epsilon times path length times concentration. So path length is going to have units of centimeters. Concentration is units in molarity, which is why we can use inverse centimeters times inverse meters and end up with no units whatsoever for absorbance. Okay. Now, as we move down this worksheet, I've broken this experiment into a total of 5 different parts. And the first part is generating a new standard curve. Now, the reason that we're doing a new standard curve, 1, so that you get more experience developing a standard curve. 2, we're using a different instrument. You're going to be using a biorad spectrophotometer. I want y'all to be comfortable using one or the other because, well, 1, the spectrophotometer that we used last week is only a visible light spectrophotometer. Whereas this biorad spectrophotometer that we're going to be using will go into the UV range or UV light range. So make sure that you're comfortable using this. And I'm going to be posting another video showing you the sequence of buttons that we're going to push for this and everything like that. Because we're measuring 2 different wavelengths. For this part 1, we're measuring absorbance at 595 nanometers, which is in the visible light spectrum. Later on, we're going to be measuring absorbance at 340 nanometers, which is in the UV spectrum. Now, for this standard curve that you're developing, you have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 and 11 are on the next page, where you use 10 and 0, where we have an entire range of the stock sample, the stock protein, and water. One thing that we have fixed amongst all of these samples is we have a fixed volume of the Bradford reagent. We have 900 microliters in there. This column down here, concentration, well, you're going to have to work down on that. So when we have 100 microliters in our protein fraction, well, we have a concentration of 10 micrograms per microliter. When we only have 90 microliters of that 10 microgram per microliter fraction in 100 microliters in our protein fraction, well, then our concentration is 9. So we reduce our concentration, our protein concentration, very gradually through this process, rather than doing serial dilutions. So I'd like you to be familiar with this different instrument, this biorad spectrophotometer, but also this different way of doing a Bradford assay by instead of doing serial dilutions, we have a more gradual dilution process. Okay, so that's part one. You're going to graph that, you're going to generate that graph, and you're going to need that graph for looking at part two, or the results of part two. So kind of at the lower portion of your page here, we've got part two, concentration of enzyme in your fraction. So first and foremost is your protein volume. Next is DH2O, and then finally your Bradford reagent volume. What you need to do is have the exact same Bradford reagent volume, 900 microliters. What I would recommend for these three trials right here is have the same volume of your protein sample and, the same amongst all three of them, and then have the same volume of DH2O amongst all of them. So what that means is you could do 90 microliters of the protein and 10 microliters of DH2O, or you could do 50 and 50. You want to make sure that you have a total volume of 1,000 microliters or 1 milliliter, and you want to make sure that your Bradford reagent volume is fixed, because then you can reasonably, or you can with a high level of confidence say that the results that I get from my enzyme fraction analysis are comparable to the results that I get from my standard curve development. So you'll get the absorbance at 595 from these samples. You'll calculate an average of those. Then, whenever you've produced your graph, you'll be able to plug that absorbance at 595 in and calculate the concentration, therefore calculate the average concentration of those samples. You would expect the average concentration to be, well, the same. You would also expect the absorbance at 595 amongst all of those samples to be the same. Okay, now part three of our procedure requires us to determine the proper amount of enzyme to use in each one of our assays. What we are going to do is we're going to try a total of 3 different volumes, and we're going to do each one of those different volumes 3 times. So what you will have is in either a test tube or a cuvette, but ultimately in a cuvette, you will have a mixture of 600 microliters of the CAPS buffer that we previously produced, 150 microliters of the NAD plus solution, and 150 microliters of a lactate solution. You'll mix those 3 solutions together. Then the last thing that you're going to add is 100 microliters of your enzyme. You will do that 1, 2, and 3 trials. 3 trials of this. You will observe the absorbance at 340 at 0 seconds, 15, 30, 45, and 60 seconds. Our expectation is that this value is going to increase, because what we're expecting is more NADH is going to be produced given more time. Okay, so that would be looking at your data for delta A340 per minute for the 100 microliter enzyme fraction. Now, volume number 2. Well, in this case, you're going to change the mixture. You're going to put 625 microliters of CAPS, 150 microliters of NAD plus, 150 microliters of lactate. And then the last thing that you're going to add is 75 microliters of your enzyme. You're going to do that 1, 2, and 3 unique times. You'll measure the absorbance at 0, 15, 30, 45, and 60 seconds. Again, we expect that our absorbance our absorbance is going to increase. We're measuring at this point absorbance at 340 nanometers, just like we did with enzyme number 1, or enzyme volume number 1, because we're measuring, so that's in the UV spectrum, we're measuring the production of NADH. We would expect that to gradually increase over time, but based on the amount of enzyme, we would expect it to have a different result. The final combination has 675 of the CAPS, 150 of NAD plus, and 150 of lactate. All after that's said and done, 25 microliters of the enzyme is added. You'll measure that 1, 2, and 3 times, and then you'll see basically how that increases over the course of 60 seconds, measuring at 0, 15, 30, and 45 seconds. All right. The second to last part is doing some calculations. Now, these calculations are very similar to what we did in class, where we're taking our delta A340 per minute and converting it to micromoles per minute. The reason that we're doing this is because we have a standard of 1 micromole per minute of NADH is the standard unit for lactate dehydrogenase activity. So I'm going to walk through a hypothetical calculation. So the way that we're going to approach this is we're going to take our 60-second time point and subtract that from our initial absorbance reading, the 0-second time point. So let's say hypothetically that we have an A340 at 60 seconds of 0.295. And then at 0 seconds, it measured 0.003. What that means is that we have a delta A340 per minute of 0.292. Okay, so 0.292. That's per 1 minute. I don't really have to worry about my time factor though. What I can do is use the Lambert-Beer law, A equals ELC, and all that I need to do is I need to rearrange this to solve for concentration because I have my extinction coefficient, I have my path length. So I'm going to say A divided by epsilon times L equals C. So my absorbance delta, or my delta A340 of 0.292 is equal or divided by 6220, which is my extinction coefficient, times 1 gives me, I'm going to use my calculator on my computer, 0.292 divided by 6220. That gets me a value of 4.695 times 10 to the negative 5th. What are my units? Well, I just solved for a concentration. My units for concentration in this case are molarity. Now that I need to get from molarity to moles. Well, molarity is moles per liter. So all that I need to do is multiply this by a volume. Well, what volume was my overall reaction? My overall reaction was a volume of 1 milliliter, or 0.001 liters. As soon as I do that, basically my calculation is ready to go where I can solve for moles per liter. So 4.695 times 10 to the negative 5th times 0.001 is going to give me a value of 4.695 times 10 to the negative 8th moles. That's close. I have this many moles per minute, but that's not really what I'm looking for. What I'm looking for is this right here, micromoles per minute. Well, the good thing about this is I know that in 1 mole, there are 1,000 millimole. I also know that in 1 millimole, there are 1,000 micromole. And this would land at micromoles, which is where I need to go. So 4.695 times 10 to the 8th times 1,000 times 1,000. That's going to give me a value of, I'm going to write it down here, 4.695 times 10 to the negative 2nd micromole per minute. And I can add that time factor back in because I knew all along that I was dividing this by minutes. So this is the same as 4.695 times 10 to the negative 2nd units of LDH activity. This is great. This calculation is effectively done. You need to do that for all of the other values. Now, I'm sure that there's some folks out there who are Microsoft Excel wizards and they can just plug in this to some sort of formula and donezo. More power to you. I'm not a Microsoft Excel wizard. The last part is something that we actually didn't really talk about, but it's something that you're totally capable of doing. Okay, so what I had, which I kind of regret erasing it, but what I had earlier was 4.695 times 10 to the negative second units of LDH activity. Or if I didn't write that, whatever number that I had up there previously. We're going to use that to calculate this value right here. Specific activity. Specific activity is units of enzyme per, well, mass of total protein. Now, we're going to say 4.695 times 10 to the negative second units of activity. We're going to relate that to the total amount of protein that was in our mixture. Now, we have our concentration of protein that was in our sample, which we collected or which we got from the standard curve that we developed, and then plugged in the values that we got for part 2. So think about this as this is coming from part 2. The enzyme volume, this is from part 3, where we tried 100 microliters of the enzyme, 75 microliters of the enzyme, and 25 microliters of the enzyme. So let's do a hypothetical calculation with this units of LDH activity that we just calculated. Let's say hypothetically that our enzyme concentration was 0.646 micrograms per microliter. And that would have been figured out in part 2. Now, in part 3, well, we had either it was 100, it was 75, or 25 microliters. Well, enzyme volume number 1 was 100 microliters, the very first part of part 3. So my enzyme volume is 100 here. And actually, if you wanted to, you could go ahead and pencil in everything else. Okay. So what this gives me, though, is it gives me a way to calculate the amount of enzyme present in my fraction. So I can take my volume, multiply it by my concentration, and get 64.6 micrograms of protein. I can then solve for my specific activity, which is 4.65 times 10 to the negative second divided by this value right here. So 4.695 times 10 to the negative second is, calculator, why have you failed me? 4.695 divided by 64.6, and that gives me a specific activity of 7.267 times 10 to the negative fourth. Now, whenever you solve for that, you do the exact same thing for volumes 2 and volumes 3. Once you've done all that work, there's a space below for you to reflect on your results and provide some sort of commentary. Do your specific activities, do they differ? How much do they differ? Are they identical? Why do you think one is higher than the other? All right, well, I hope that was helpful, and that's what we've got for this upcoming week's experiment. Look to your Canvas page for some videos walking you through how to use the Bio-Rad spectrophotometer, though. All right, well, have a good one.